Hello, everyone, and welcome to this month's Insights in Practice webinar from Microbial Insights. Today, we're joined by Dr. Brant Smith from Evonik for this presentation titled Methods for Combining In Situ Chemical Oxidation and Bioremediation. Our speaker, Dr. Brant Smith, is the Technology Director for Soil and Groundwater and Persulfates with Evonik Active Oxygens and has over 20 years of experience designing and implementing in situ chemical oxidation, reduction, and bioremediation at bench and field scale. He has authored over 80 national and international presentations and numerous journal articles, and has served as co-principal investigator for a CERTIP research grant focused on ISCO. MI's webinar sessions this summer have really investigated the strengths and strategies for combining multiple cleanup technologies. We've talked about abiotic-biotic approaches, ISCO, and today I'm excited to dive into the synergies between ISCO and bio with an ISCO expert, Dr. Smith. Before I hand this over to our speaker, I do just have a couple of reminders. First, at the end of this presentation, we will take our remaining time for a Q&A session. So please type your questions in the GoToWebinar control panel and we'll get to as many of those as we can. This session is being recorded and the recording will be available on our website as well as on our YouTube channel in the coming days. You can also subscribe to our YouTube channel to keep up with future webinars as well as our MI video series. Finally, certificates of attendance and a survey will be automatically emailed tomorrow to all attendees on stream right now. Now, please join me in welcoming our speaker, Dr. Brant Smith.
Thanks, Hannah, and thanks, Dora, for letting me present today. As Hannah was mentioning, I'm going to be talking to you about the methods for combining in situ chemical oxidation and bioremediation. Very quickly, I wanted to go over, of course, I'm with Evonik. I'm the Director of Technology of our group. We have a number of different products. Most of you, I'm sure, are familiar, but this includes chemical oxidation, aerobic bioremediation technologies, enhanced reductive dechlorination technologies, chemical reduction, metals stabilization, and then, of course, biogeochemical reagents that are used to remediate chlorinatids. I'm actually going to be talking about a number of these different reagents today because, of course, the focus here is on how these technologies can be combined, both naturally, but also intentionally as you mix and match the different reagents. Overall, I'm going to be going through ISCO and in situ chemical oxidation and in situ bioremediation, some very quick definitions. I'm going to actually be pulling this back and talking about a few fundamentals. It's going to probably be a rather basic for a few of you, but once you get back to some of the fundamentals, I think you can understand some of the points that I'm trying to make here. These fundamentals are going to be talking about the oxidative and reductive pathways, abiotic versus biotic reactions. And then we're going to be talking about the impact of persulfate on microbial populations. And really, you'll see a couple of the studies. They're talking about ISCO overall. Then we're going to talk about bioremediation that follows ISCO naturally. Then combined remedies, sequential applications, and then, of course, what presentation would be complete without a summary. Very quickly, in situ chemical oxidation is the addition of thermodynamically powerful electron acceptors. It works via an abiotic pathway. These can be used to treat a very wide variety of different contaminants of concern. It tends to be very fast reactions. When you look at some of the radicals that are formed with activated persulfate, the persulfate will persist for weeks to months itself in the subsurface. But as you form those radicals are typically persistent for less than a second, usually nanoseconds. They react very, very quickly. You can also, with ISCO, get a lot of this electron acceptor, these thermodynamic powerful electron acceptors into a single application. This makes it ideal for people that want to move quickly, remediate things, and understand what they accomplished, in short order. And it is ideal for source zones and mass removal of significant amount of contamination. Bioremediation is, also a very well-established, powerful remediation technology. It typically is the addition of electron donors or electron acceptors that treat contaminants via a biotic pathway. Okay, so this is microbe or fungi mediated. This typically occurs over an extended time frame, and extended can mean different things to different people. We have seen some technologies that can be relatively fast acting and getting especially when bio-augmented, becoming active within a few months. But oftentimes you will see ISB effective over a period of at least a few years. This is ideal for treatment of plumes and polishing applications, but of course has also been used to go after some source areas when immediate treatment was not necessarily required. Okay, oxidative and reductive pathways. For those of you that remember Dan Lay, who recently retired, this is what we called a Danimation. He was very skilled at creating some of these. But this is just going over what an oxidative and a reductive pathway are. Oxidation is the loss of an electrons and an increase of an oxidation state of an atom. And almost always we're referring to carbon. So you're increasing the oxidation state of the carbon. It is losing electrons. It actually is an electron donor, and this is why we add these electron acceptors. A reduction is a gain of electrons or a decrease in the oxidation state of an atom. So when you're doing a reductive reaction, you're typically adding something that is donating electrons. And Dan created this little visual where you have, it's always a coupled reaction. You always have an oxidizing reagent and a reducing reagent. And as these things collide and react, the electrons are transferred from one to the other, okay? So basically, in here, the little ball A is oxidized and the ball B is reduced. If you were to look at this in terms of treatment with ISCO, for example, the oxidant is actually going to be like a persulfate, and it takes the electrons away from the contaminant. So the contaminant becomes oxidized and the persulfate actually becomes reduced. These pathways are critical, and it's usually almost always step one when you're trying to assess a site. You're looking at what your contaminants are, and not all of them can be treated by every technology. You have oxidative pathway, contaminants that can go via the oxidative pathway. You have contaminants that can go via the reductive pathway. Then you have contaminants that can go either with the footnote, of course, that sometimes this requires the hydroxyl or sulfate radical from ISCO. Aerobic bioremediation does not necessarily treat all of these contaminants that I have listed here going oxidatively or under either. This is more based from the ISCO perspective. So why is oxidative and reductive important? Understanding the pathway, understanding what you're trying to do out there. It really is fundamentally a 1 or a 0. Will your contaminant be treated, yes or no? So it's one of the most critical things that we can do when assessing a site. Getting to abiotic and biotic pathways. I actually, every once in a while, I like to dust off some of the technical books that I have. In this instance, it was the McGraw-Hill Dictionary of Scientific Terms. Biotic is induced by the actions of living organisms, in this case, microbes or fungi. Abiotic is referring to the absence of living organisms. So some quick examples, when we talk about a biotic pathway or bioremediation, we're talking about something where the electron donors and the electron acceptors, basically, that's one part of it, but the other part is that the reaction is mediated by microbes or fungi, usually one or the other. Abiotic, you're talking about something that can react on its own, and this is ISCO. In this instance, I'm going to be talking to you about persulfate, and zero valent iron would be an example of a abiotic pathway that's a reductant. It can donate electrons, reducing things. Staying very much in the basics, a basic reaction you have, and this is what the Danimation showed, where, you have an electron donor and electron acceptor. Those two react and you end up with the products. With ISCO, you're talking about an electron donor being the contaminant. So the contaminant itself is the electron donor. The oxidant is the electron acceptor, and you get this reaction and the contaminant is oxidized. Oxidative bioremediation, you're usually, again, the contaminant's the electron donor. The electron acceptor is usually oxygen, but we're going to talk to you a little bit about other electron acceptors, in this instance, sulfate. And then you can have these reactions that are mediated by microbes and fungi and get products. Reductive bioremediation, you're talking about you're adding typically an electron donor. Contaminants are the electron acceptor, and you're basically you're adding electrons to those contaminants, getting products. So looking at this a little bit more conventionally, when you're talking about adding things, you can have bioremediation, electron acceptors of oxygen, sulfate, chemical oxidation. You can get iron chelate, permanganate, hydrogen peroxide, iron chelate activated persulfate. Bioremediation, an organic electron donor. In the instance of Evonik, REHC has an organic electron donor, a solid organic electron donor. We also have ELS. For in situ chemical reduction, there's of course biogeochemical with the iron sulfides and zero valent iron. Interestingly, just because persulfate and peroxide are powerful enough to oxidize water. You can actually get a reductive pathway in and from these oxidants with alkaline and hydrogen peroxide activated persulfate. So you actually get both pathways with alkaline activated persulfate, although the predominant pathway is still oxidative. What does all of this mean to this presentation today? One of the principles that I'm going to try to articulate is the fact that when you're applying ISCO, you are actually changing the geochemistry of the site, even though temporarily, because of course, the overall site geochemistry will eventually win out. But you are creating these additives. You're adding with persulfate, it decomposes from sulfate, so you're adding quite a bit of sulfate. You're adding and altering often the pH. One of the things, though, I want to introduce, this concept that I want to introduce to all of you is that oftentimes you're also oxidizing more complicated organics that could just be soil organic matter. Sometimes it's the contaminant, but you will be, when you oxidize something, you're adding oxygen to it. You can be creating alcohols, you can be creating carboxylic acids. This makes those organics more soluble, and you often see a spike in dissolved organic carbon within the aquifer after applying ISCO. This can be used as an organic electron donor. So again, stripping things back to their fundamentals, looking at this, just applying ISCO, you're actually usually adding electron donors into the subsurface that can react after the application. We're going to be talking about that. So before we get too far, there are still some people out there, despite the evidence, that think ISCO might sterilize a subsurface. So let's talk about the ISCO's impact on a microbial population. We can go back to, even as far back as 1998, 1999, early 2000s, and there were actually studies out there showing that bioremediation could be occurring in the same time as chemical oxidation. In the actual reactors, they were finding evidence of both bioremediation and chemical oxidation. This is mostly with hydrogen peroxide, but they were actually finding both these reactions occurring at the same time. Okay, so does ISCO sterilize something? In fact, bioremediation can be occurring simultaneously with chemical oxidation. A few years later, there was this summary article that looked at a number of different sites and basically found that microbial activity, the population, was enhanced following ISCO. And you're going to see that trend again and again as I present the actual site information. And the effects of this, it takes a little bit of time, but you usually see this recovery and enhancement to the microbial population anywhere from a few weeks to up to a year after the application. Getting into some of the data, the top right graph is a closure CR, different dosages. And as you can see, with increasing dosages, and this is kind of the pattern that you're going to see again and again, you do negatively impact the population typically for a few weeks, maybe a few months, but then it recovers. And that's a lot going on there in that chart. But if you focus in on the circles that are hollow, that are not solid filled, you can see that the control basically stayed in there around 5 log MPN per gram soil, very consistently across the board, and somewhere between starts even at 4 weeks for the lower dose, all the way up to about 12 weeks for the highest dose, dose 3. So dose 1 was the lowest dose, and dose 3 was the highest dose. You can see where the microbial population crossed the line of where the control was, and actually you had a greater microbial population in each of these test conditions applying closure CR. If you look at the more of the center but bottom figure, you can be looking at, you see the same kind of dip. It's a hard dip right out of the gate in terms of microbial counts, colony forming units per gram. And this is looking at fentans, modified fentans, permanganate, and alkaline activated persulfate. That's what the A-PS means. But then you can look at, and by 18 weeks, all of them are starting to recover. And if you look at a couple of them, even by 24 weeks after the fact, they are starting to get at least the hydrogen peroxide, the fenton reaction, and the alkaline activated persulfate are actually getting to be at the same level they were before, or even higher than what they were at baseline. Okay, so bioremediation following ISCO naturally, without doing anything else. Let's talk about this. So biotic activity is almost always occurring. I'm not sure I've ever heard of a sterile subsurface. So it's more of just really beginning to understand that biotic activity is occurring at all times. applying ISCO will alter the baseline geochemistry. So basically, you're going to have a status quo, and you're basically going to disrupt that status quo with an ISCO application. And one of the things I'm going to show here is that bioremediation has been observed to occur following ISCO if you take the time to monitor for it. And so that's one of the other themes I want to talk about. Basically, that monitoring is pretty critical. Focusing in on persulfate, the residual is going to be sulfate. Sulfate can be an electron acceptor. This is anaerobic oxidation. This basically requires an electron donor. So if a site stays oxidative, you're not going to automatically get sulfate reduction because you need to be, reducing ORP before you get the sulfate being reduced to sulfide. But once you get to that stage, it's actually a very beneficial electron acceptor because it can accept, each molecule of sulfate can accept 8 electrons going all the way to sulfide. And for those of you that pay attention to the electron potential of different compounds, 8 is a big number. But then you can flip it around, and as I was mentioning earlier, there's an electron donor potential that has also been observed. So this is a different pathway. An electron acceptor, of course, is going to be working to oxidize your contaminant. An electron donor is going to work to reduce your contaminant. And this comes in the form of dissolved organic matter that can spike. And again, this is something that you need to observe, usually looking at ORP post-ISCO. The other thing ISCO can do is release a series of different nutrients. And again, you're disrupting the status quo. You're oxidizing things, partially oxidizing things, adding oxygen groups to organic matter. If organic matter was covering something up, the surface of something, it's being oxidized, pushed to the aqueous phase, all of a sudden fresh soil is exposed. But the bottom line is you can also see a spike in nutrients following an ISCO application. But really just focusing in on the electron acceptor by, adding in sulfate, and then the reductive dechlorination that you can get by the increase of nutrients in dissolved organic matter in these next couple of slides. There have been a number of people that have looked at a site and the different parameters. Masha Shannon's article, 2017, she did that up with Neil Thompson up at University of Waterloo. She tracked, it was a field test. They created a box basically and tracked the ISCO zone to the anaerobic oxidation zone. That article is out there. I'm focusing more on some work that Nora Sutton did during her PhD. This is 2014. There's actually 3 good articles, at least ones that I like. There might be more from 2011, 2014, and 2015, looking at different things. This 2014 article looked at creating a pilot test box. So it's a field application. 25 cubic meter or square meter box. And when you look at the arrows, the 2 dark arrows are persulfate applications. And then the gray arrow was, if I recall correctly, a nutrient addition. And what you can see is that after, and then there's within the radius of influence of the injection wells, downstream and then upstream are the 3 different columns that you can see there. What you can see is what you would expect. You add something that's a salt, persulfate, an activated persulfate in this instance, and you see a spike in conductivity. This is very typical when you watch Josephine or my presentations on monitoring. This is one of the first things that we look for is the spike in conductivity. You also see this nice spike. You went from an ORP of -100 all the way up to ORPs pushing 500. Okay, again, typical. This is what you would expect. Then you can look at the pH. And again, this is unactivated persulfate. We tend to do, or the industry tends to do more alkaline activated persulfate than anything else. So actually pH would typically go up because of the alkaline activation, but persulfate forms acid. And so if you have unactivated persulfate, you can see this dip after an application. With alkaline activation, we dose trying to get a spike. And then as persulfate decomposes, it releases the acid and it neutralizes the alkalinity that you add. And, I've seen a couple sites, what I would consider to be typical is ending up with somewhere between pH 6 and 9 at most sites. But then I want you to move down a little bit. The bottom 2 rows, you look at dissolved organic carbon, and you can see it spiking both within the target area, the ROI, and you can see it spiking downstream. But then also looking at total bacteria. And again, this is looking more at gene copies. You see a slight decrease, but you see a recovery. So here you didn't see an enhancement, but you did see the recovery, again, talking about how, or illustrating that ISCO is not necessarily hurting the microbial activity. Getting back and focusing in on the sulfate reduction a little bit more, just want to make the points that basically when, if you were to do sulfate reduction in a laboratory setting, where you would expect to see it is around an EH of negative 220. What we tend to see in the field is higher than that. And that's simply because most monitoring wells, well, all monitoring wells are a composite of their screen interval. And usually you'll get little nooks and crannies within an aquifer that are more reducing than the preferential pathways. Therefore, in those nooks and crannies, it might be more reducing than the overall flow that's being represented going into a monitoring well. So once you start getting below negative 100, negative 200 in actual field conditions, that's when we start to see sulfide evolving. So concrete evidence that you're getting sulfate reduction. The other thing I want to emphasize here is that while the potential is great because of that 8 electron transfer, thermodynamically this is not powerful and all that powerful. So it only reacts with certain oxidizable hydrocarbons. I want to say toluene is at a BTEX is preferentially treated, but it does and it will react with PAHs and other petroleum hydrocarbons. The reason for this weakness is just the fact that it's as you go down the electron tree, sulfate reduction is pretty low. So the microbes are not actually getting that much energy from the sulfate reduction. The other thing I want to note here is that you can actually look for this, not only look for it in terms of your the sulfide evolution, but you can actually look at the ratio if you monitor for both sodium and sulfate. The bottom line is sodium is going to be conservative, and sulfate has a couple of different fates. And so that ratio could go from the, persulfate, when you break it down, it's 19% sodium and 81% sulfate. As you break that down and sulfate, something's happening to sulfate, of course, you'll get more and more and more sodium. That ratio will begin to favor the sodium. A few more laboratory studies, and there was actually a lot of recent laboratory studies on this by the last 10 years. I really was tempted to include a lot more. But this is the one that I picked. This is out of Dan Cassidy's lab out there at Western Michigan University. This was presented at the 2019 MGP conference. The bottom left figure is looking at the qPCR and the 16 sRNA group. And this is why I'm very happy Dora is going to be helping answer questions, because I can say those words, but I think other people in the industry understand it a lot better than I do. But basically, this is looking at the gene, the groups that are being formed. And you can see here, again, there's that little dip. And this is in months. So again, that little dip is occurring for each one of these in the period of weeks. And then once you start getting into the couple of months, everything is recovered. And it's not only recovered, again, what is being observed is that each of these is actually higher than the control, okay? And this is actually kind of interesting. Dan did a lot of ISCO ISS. So I want to emphasize how extreme these reactors went through. This is both using the alkaline activated persulfate based on the binder that was added, the Portland cement. These were solidified into monoliths. And then basically Dan put them into a dark room for a period of time and just continued to monitor, every couple of months and just to observe what was going on. So these have been, these microbes have been exposed to high pH. These microbes have been exposed to the oxidant, and they are coming back strong within about 4 months, maybe 6 months. They are back and going. Now, looking at the figure over to the right, what you can see is treatment of naphthalene. And he looked for naphthoic acid, 1 naphthoic acid and 2 naphthoic acid. And so these are decomposition products of naphthalene. And what he saw was a classic figure. He saw the iron 2 going down. So that's the iron reducing bacteria, reducing the iron 2 to iron. Well, actually, so the iron 3 went to iron 2. And then the iron 2, as the sulfide went up, the sulfate reducing bacteria kicked up. And this is the red. The sulfide went up. The iron 2 precipitated and formed iron sulfides. And so you can see both of those going down eventually by 20 months. And you see this nice steady concentration of the naphthoic acids. Has this been observed in the field? This is actually one of my sites. And this was a straight up alkaline activated persulfate application. It was in New York City as a high rise was being built. We went after the subsurface, going after petroleum hydrocarbons, GRO, DRO, benzene, naphthalene being the primary goals, hit it with 33,000 kilograms of alkaline activated persulfate. Remedial goals were met, no rebound was observed, and no further action was granted at the site. But the data is actually very interesting. You see sulfide precipitate formation, you see sulfate going down, you see ORP into that -100, -200 range that we're talking about, and we see BTEX and naphthalene continue to diminish. In other words, this to me has all the earmarks of anaerobic oxidation occurring at that site. So the other mechanism that we're talking about is that organic matter from a variety of sources can be oxidized and can move into the aqueous phase to be readily, to basically feed the microbes. It becomes an electron donor for the microbes. They use it up and move you into reducing conditions. The oxidizable material can come from the contaminant, or it can also be a portion of the soil oxidant demand. Bottom line is soil oxidant demand when you're doing an ISCO design is usually measuring a combination of reduced metals, but also oxidizable organics. And almost all sites have some measurable amount of soil oxidant demand. Has this also been observed? And the answer is yes. You can go back to early 2000s. This is Ed Drosty. This was an application at a site, I believe in Ohio, where they were going after TCE NAPL with a combination of applied persulfate and permanganate. The DOC is thought to have stimulated the reductive dechlorination. And when you do the math, as you can see in this one chart, and this is a Battelle presentation from 2002, so it's out there in the public domain at this point on their website, you can see that there's basically two distinct periods. There's the distinct period really from the two first rows from August 99 to March 2000, where ISCO is being applied and they measured and quantified the chloride and the equivalent amounts of TCE being treated. But then there was a lull for a couple of months from March 2000 to June 2000. And then from June to September 2000, all of a sudden, as the geochemistry shifted, you started seeing all of this additional chloride being produced. And there were a few other parameters that they looked at, but the conclusion was that the spike in DOC stimulated reductive dechlorination of the TCE, and you saw additional treatment. About 33% of the additional treatment was from this treatment, the bioremediation following after this ISCO application. Okay, so that's what can happen and has been observed to happen following ISCO applications. But let's get real. ISCO and bioremediation have been combined together intentionally using a lot of different techniques. First and foremost, combining, we have this product, Closure CR, have for decades. Like I believe it's 20 years old or 22 years old at this point. This is a 50-50 blend of Closure SP, so sodium persulfate, and Permeox Ultra, which is calcium peroxide. Okay, so you end up getting the three mechanisms: ISCO, aerobic bioremediation, and anaerobic oxidation following the addition of this product. We tend to think the ISCO persists for a couple of months. The aerobic bioremediation can persist 6 to 12 months. Often used to go after petroleum hydrocarbon sites with moderate, less than say 100 milligram per kilogram concentrations. Okay, but there's the real benefit here is there's three remedial pathways in a single application. So these are chemically compatible. They can be and are applied together because Permeox is a solid or extremely low solubility. It's applied as a solid slurry. So again, this is a combined remedy: ISCO, aerobic bioremediation, anaerobic oxidation. And the little schematic we have here that we often apply or show to illustrate this is that you have a source zone that is treated both by ISCO and aerobic bioremediation and the sulfate reduction. Then as you move down gradient, the oxygen migrates and it treats a little bit of not only the surface area, but more down gradient as the oxygen migrates. And then the sulfate, which will persist even longer than the oxygen, as you move down that electron tree, it will move further down gradient and be an electron acceptor for sulfate reducing bacteria in that area. This has been used extensively, and I'm going to use just two illustrations instead of a single case study. This was a figure that Alberto Liambruni created. He's our manager over in Italy. Basically, he had Closure CR being applied from 2017 to 2024 at 286 sites. And so when you start getting this kind of density of data, you can start looking and seeing how well things are looking. 65% of the sites were closed after a single application of Closure CR, again with the three pathways. as long as you're using it to treat an appropriate amount of contamination, very, very effective. Then a second application was required, and another 25% of the sites were remediated. The additional 10% of the sites required additional reactions, either due to unexpectedly high concentrations, soil conditions. Clays are of course more difficult to treat than sandier materials, but only 10% of those sites required additional treatment or more treatment than the two applications. This has also been observed in Vancouver. This is courtesy of Jean Perret and Chemco, but they helped support a contractor that was working over in Vancouver from 2015 to 2021. They applied Closure CR at 150 locations, petroleum hydrocarbon locations. 148 of those sites were successfully closed. So again, this has been used extensively, going after typically petroleum hydrocarbon sites, although alkaline activated, hydrogen peroxide activated persulfate will give you the reductive pathway. So if you have low levels of certain chlorinated compounds commingled with petroleum hydrocarbons, talk to us. This is potentially on the table, but you can basically combine to go after different types of contamination. You can combine permiox or calcium peroxide with persulfate very effectively. And just to kind of summarize this, we really like this product going after these low levels of contamination, moderate to low levels of contamination, largely because you get the three pathways. And so you get, kind of the iterative approach out of a single application. You get ISCO, that's typically active for 2 to 8 weeks. That's going to, treat the largest amount of your contaminants. Also, it treats things that might be binding your contaminants. And so you get this desorption effect. You have the aerobic bioremediation that can occur after the ISCO, typically up to 9 months, maybe even up to a year that you'll have that be active. And then bioremediation with anaerobic oxidation, the sulfate reduction. All of this has to be monitored. You should be looking at your ORPs. You should be looking at your DOs. You can be looking at, sulfide, sulfate, all of those kind of compounds, other electron couples, iron 2, iron 3, all of those to kind of understand where you are in the process. Sequential applications. This is actually probably what most people think of when they think about a combined remedy. The bottom line is that persulfate is often used to go after higher concentration areas, but then you can apply, in situ bioremediation products. Say if you're going after NAPL levels of chlorinateds, you can do that with persulfate. And then, as you looking more at residuals with the chlorinateds, you can be going to an ELS or an EHC. With petroleum hydrocarbons, you can be, of course, going after the more, say if you have an MGP site, you can be treating the higher levels of contamination with persulfate, and then you can be pivoting to Closure CR or Permiox Ultra. This can happen sequentially in terms of going after a source area and then polishing it as the concentrations are reduced, or it can happen spatially as you treat the hotspot or the source area with ISCO, and then the plume with some sort of bioremediation. So this is a quick illustration. This is probably the most common method, but ISCO is used to go after the higher levels of contaminant concentration, which would be, in this instance, the darker color. Once it's effective, of course, you've knocked down the contaminant mass significantly, and then you go in with the polishing step and use bioremediation to polish out the additional contamination. And then hopefully, all things working as they should, you would be achieving the remedial goals and having cleaned up the site. The other sequential application is, of course, spatially. I borrowed the figure we use in Closure CR, but basically you could use ISCO to go after the source area, again, likely based on some sort of concentration, but it also could be the type of contamination that you're going after. Quite often there are certain contaminants that will only be treated by ISCO and not necessarily by even aerobic bioremediation. That list gets smaller as you pivot to aerobic bioremediation, and the list pivots to even smaller list as you go to anaerobic oxidation. So you can go after either concentration-based, soil type-based, or contaminant-based source area treatment with ISCO, and then pivoting, depending on what the plume consists of, into ISB. And if it's chlorinateds, of course, you can pivot to EHC and ELS and other electron donors, biogeochemical. And actually, this is one of the points I want to make, but if you do a source area treatment with ISCO, you can watch and maybe even wait for that sulfate from the persulfate to migrate down into your plume and create biogeochemical conditions if you have enough electrons to donate to reduce the sulfate to sulfide and enough iron in the subsurface to precipitate that into an iron sulfide. And the real benefit there is that you basically create something that's going to coat the walls of the preferential pathways that will persist for years and years and continue to treat the contaminant as it migrates into that area if you have a contaminant that can be treated via the reductive pathway. An example of this is a sequential, same area. ISCO was used to treat NAPL levels of contamination. This is, again, one of the sites that I've worked on in the past. But ISCO, hydrogen peroxide, and then activated persulfate was used to reduce NAPL level concentrations down to, if you look at the graphs, part per billion levels. So we went from milligram per liter levels down to part per billion levels, about 70% of the mass. But there was clay lenses, there were sandy areas, and then there were clay lenses. To address the back diffusion coming out of low perm, we transitioned to bioremediation. Our Battelle transitioned to bioremediation. This is Steve Rosansky with Battelle out there at Alameda. And basically, they observed the formation of biogeochemical conditions. And this included confirmation that the iron sulfides were being formed. That you can see they even took the time to make the pictures and do the analysis to confirm the precipitation of the iron sulfides. If you look at the table on the top right, you can see that there was significant reduction. So you're off the charts on that table when before the ISCO was applied. I want to say it was in and around 20 milligrams per liter or thereabouts. Then we, through the ISCO, we got it down to this 100 to 120 to 140, I guess even 100 to 140 pre-reductive. And then after the reductive, you can see that we're down into the low, really non-detect to in and around by the April 2011, less than 10 part per billion concentrations. Okay, so in summary, and the first thing that I'm going to summarize is all of this has probably been going on at most of the sites, and there's thousands upon thousands of ISCO sites. But oftentimes ISCO monitoring programs are really designed just to look at, contaminant, destruction shortly thereafter an application, not necessarily looking to see what's happening to the microbial population, not necessarily looking to see what may be going on with the contamination, even the low levels, residual amounts of contamination after the fact. And the fact of the matter is bio is almost always going on. Bio, the microbial population usually, dips just a little bit when you have ISCO going on. But as you can see from the different examples, and there's even more examples out there, it dips, and then with a matter of weeks, maybe a month or two, it does recover, oftentimes higher because you have the increase in dissolved organic carbon, plus you have the increase of nutrients and the increase of sulfate for your sulfate reducing bacteria. So this is just a general guide of what we'd like to look at. If you want to look at following a persulfate application and see if anaerobic oxidation is occurring, looking at sulfate, sulfide, and sodium would be great things to look at. But also maybe looking at the microbial population, maybe also looking at dissolved organic carbon. All of these things can help you understand what's going on at your site. And then the true summary, biological activity following ISCO is almost certainly occurring at many, if not all sites. Will the monitoring program that you've created capture these effects? This can affect both chlorinated and hydrocarbon compounds, depending on, if you're creating the reductive pathway with the dissolved organic carbon, or if you're getting anaerobic oxidation and additional treatment of your petroleum hydrocarbons. Bioremediation can be planned as well. Closure CR is an entire product that we created out of the concept that that calcium peroxide and persulfate can be applied in a single application to give you three pathways to reduce your contaminant concentrations. So this is a great way to go after petroleum hydrocarbon sites in particular, but it has also been used to go after sites with some levels of chlorinated. That's something that we can talk about if you are curious. So with all of that, I would like to wrap up my presentation and take questions. And I also just want to emphasize, that you can reach out to me, anybody with Evonik, but especially Josephine Moline, who's the technical manager for in situ chemical oxidation for our Evonik soil and groundwater group, and is even more and better versed than myself in biotic activity. So with that, I'll turn it back over to Dora and Hannah for questions.
All right, thank you so much, Brant. That was an excellent presentation. We do have a few questions, and for everybody out there, if you have additional questions, please go ahead and enter them into the GoToWebinar software, and we'll have Brant answer them for you. So the first question here, Brant, is for chlorinated compound concentration, does the presence of high sulfate diminish the ability for Dihalococoides to be able to perform? Do you see that the sulfate-reducing bacteria will compete with the Dihalococoides?
So Dora, I'm going to absolutely want you to contribute to that in just a second. What I would say is one of the things to think about with the Dihalococoides and the bioremediation, that's definitely a reductive dechlorination kind of pathway where you need Dihalococoides to go from DCE to vinyl chloride and vinyl chloride down to ethene, ethane, those kinds of things. Dihalococoides, a number of effects a number of geochemical conditions can impede Dihalococoides. pH is probably the one that I would look at the most. But specifically regarding the sulfate, if you have sulfate there following a persulfate application, and you are forming sulfides, and you are getting the iron, if there's enough iron in the aquifer, which is quite often the case, iron is pretty ubiquitous, but especially if you went with closure 1 or iron chelate activation, you're actually adding iron into the subsurface. If you see those reductive dechlorination conditions, and if you see the sulfate reducing conditions, you're forming iron sulfides. And this creates a completely different pathway. And I didn't get into this, but there's a lot of other content out there. But iron sulfides reduce chlorinatids via an abiotic pathway that doesn't even go through DCE or vinyl chloride. It actually goes this other pathway. I'm forgetting what the name is at this exact moment. But that will end up treating your contaminants that doesn't even involve the Dihalococoides. Dora, do you want to add on to that?
Yeah, so you're definitely right. You can have abiotic conversion processes that will happen from your iron sulfide formation, and you'll get different daughter products. So that is one benefit to environments that have both iron and sulfate that is present. But, and you're right, Dihalococoides can be inhibited if your pH is not in the neutral zone. So you kind of want between a 6 and an 8. 7 is optimal for Dihalococoides to be able to grow. And then when you have areas of high sulfate, and I've been looking at sites like this for 25 years now, what we typically see is when you add some type of electron donor and get the fermentation and hydrogen is generated, sulfate reducers will start to grow and use that available hydrogen, and they'll kind of outcompete Dihalococoides for a period of time, typically 3 to 6 months. Once those sulfate reducers start to stabilize, then you'll see your reductive dechlorinating organisms, particularly Dihalococoides, start to increase. And so it gives you a lag, but it doesn't mean that it will forever outcompete them and you won't be able to get them. And actually the sweet spot for Dihalococoides is kind of between sulfate reduction and methanogenesis. So that's when you kind of get the most reductive dechlorination that we see. So I think, you don't be intimidated if you have high sulfate. You can use it to your advantage, especially if you have the iron, because you can get the abiotic transformations, but you just want to expect there to be maybe a lag phase in your reductive dechlorination. And so monitor for those sulfate reducers and monitor those Dihalococoides concentrations so that you make sure you see them increase over time.
Sorry, go ahead.
No, I was just going to say, but you're right about everything that you said on that, Brant.
Yeah, and I'm not surprised by what you said, and I think this plays into one of the things I'm trying to articulate here is continue monitoring and looking at the different time frames. The bottom line is as I said earlier on, site geochemistry is going to eventually win out, but when you go out there and you do remediation of all sorts of different types, you're disrupting the subsurface, and there's going to be all of these different events that are going to be occurring as you go back and work back towards the baseline geochemistry. And you need to basically have if you want to and care about each of these different steps, if that's important to your site, then you need to basically be thinking in terms of months to years after the application for all the sulfate to be, in this instance, using this example, be looking for the sulfate to be reduced, be looking for the iron sulfides to be created, but then be looking for Dihalococoides and the reductive dechlorination, if the chlorinated compounds are even still present, to be treated via the reductive dechlorination pathway.
That's correct. It's typically kind of a train of different technologies that are pathways that are working together that'll get you ultimately to the closure or reduction point that you want. So the next question that we have for you, Brant, is closure corrosive to underground utilities? And then there's a second part to that, is potassium persulfate less corrosive than sodium persulfate?
Yeah, I do. It can be, is the short and briefest answer. I definitely want people to proceed with caution if they think that the reagents will react with or come in contact with underground utilities. This isn't only just an evaluation of what the material constructions were for the underground utilities. It is often the case that the material construction, parts of it are chemically compatible, but where the screws, where the bolts, where whatever is holding it together. And then with some utilities, you need to factor in the fact that they included sacrificial anodes, oftentimes metallic zinc. And basically, as you are taking any kind of, this is the same reactions that we're talking about here. Again, breaking things back to their fundamentals. Zinc is going to be an electron donor. That's how it works to keep help passivate and help maintain the system. If you add any kind of electron donor, it will actually potentially consume some of that that system, that zinc that you may have there. So it is something to be evaluated going into the system. That being said, there are dozens, hundreds, thousands of sites that are in close proximity to underground utilities. I've seen people first, foremost, confirm that the injection is not going to contact, the underground utilities. This is often vertically. Underground utilities are often shallow. Contaminant is often deeper. So there's a vertical component. You can also limit it horizontally. Just make sure that the underground utilities are far away from the expected ROI, and then maybe even have some sentry wells in there to confirm that some sort of preferential pathway isn't going straight from your injection solution to the utility corridor. The other thing is, and I've worked with people to create physical barriers in between the underground utility and the application, and this can range from a physical barrier, such as a sheet piling or something like that, or it could be something like like injecting water to create a hydraulic barrier. Finally, we have also seen a lot of people go to soil mixing in and around the underground utilities. Of course, you have to, you can't soil mix through the utility, but the bottom line is an injection strategy can follow preferential pathways. Soil mixing, especially with ISCO ISS, the reagents really do tend to stay in where they're in place. So there's little concern or minimal concern about them migrating. So it is something to pay attention to. Going to the question of sodium versus potassium, really the difference between those two products, they both release to form the sulfate anion. So the oxidant is actually the same, which is why the reactive chemistry is actually the same. The big difference is that sodium persulfate has a theoretical solubility that's really an order of magnitude, more than an order of magnitude higher than potassium persulfate. So, you can be looking at a theoretical solubility of 580 gram per liter of sodium persulfate and about, 40 to 50 gram per liter of potassium persulfate, depending on the temperature of the aquifer. And so you just can get a lot more sodium persulfate out there than the potassium persulfate. So there is a benefit to the potassium persulfate, is the short answer there. Once we get closer to utilities, we often pivot from sodium persulfate, if there is a concern, if there isn't a physical barrier that we can create, sodium persulfate to potassium persulfate. Then we start even looking at permeox, because of course that will, oxygen's not going to be as thermodynamically powerful as the persulfate. So there's a lot of steps that we can take, but it is something that we recommend people that to take seriously and to evaluate.
All right, the next question is, do you have a specific combined remedy that you think works best in difficult to remediate soils, such as tightly bound clays or anything that will have a low hydraulic conductivity?
Yeah, that gets real specific really fast. I will say with clays, we often pivot quickly to one of two methods. I'll go with soil mixing first because I was just mentioning it. The limitations of a clay, once you start soil mixing, the soil mixing breaks the clay apart and you establishes contact for you. So a lot of the limitations of a clay with soil mixing go away. So we're seeing a lot of clays being treated with ISCO ISS over, the last decade. That's really something that has evolved. The other thing that we pivot to is like a fractured injection with closure KP. And, this is one of the things, there's a lot of thought that has gone into our portfolio. This is one of the thoughts, but, it's a matter of understanding what's going on with your site, understanding what's going on with your contaminant. And if they are, some sort of phase transfer limitation, or if they're distribution limited, some sort of time component, don't go in there with an oxidant that is going to be fully soluble and only active for, a week, a couple weeks to 1 or 2 months, like sodium persulfate. We have gone after low perm soils with a fractured approach with closure KP, hydrated lime as the activator, both of which can be active for, months to years, and really a couple of years. We've seen sites where, the potassium persulfate has persisted. And what that is it buys you time. And so if you have, in that time, you can allow for diffusion, which is a slow process. So you can diffuse out of the fractures where you have placed the potassium persulfate deeper into soils, but also the contaminant can migrate, depending on the flow of groundwater, can migrate from wherever it is to those fractures, because of course the fracture tends to be a little bit more permeable than the low perm soil. So you can get both going on. And so those are the two approaches that we would quickly default to without knowing any more specifics with a low perm soil. There are, of course, others. Actually, I was talking about things Josephine has done, and she's had entire presentations on how to treat low perm soils. So definitely a resource if people want to ask questions.
Great. So of the examples that you gave where you saw microbial activity rebound after ISCO, were any of those following ISCO with peroxide, or all of them were persulfate or other oxidants, is the first part of her question. And then the second one is, are the remediation amendment products typically applied with a soil aeration system like sparging or venting?
I'm going to take the second one first. I actually would I would very much recommend using dedicated and systems that are constructed to inject the ISCO reagents. Air sparging systems, if you're going to try to use them, you really do need to line up and look at the materials of compatibility, how the wells were constructed, but also your screen intervals. If you think about a sparge system, it's usually was the sparge points were put at the bottom of where your contamination is, because gases are less dense than water, and so the gases were meant to bubble up through your zone. Whereas ISCO reagents, because you're adding reagents to water, are going to tend to be more dense than water. They're going to tend to sink on you, okay? And so the bottom line is, I've seen people try to use sparge systems to go after the treatment zone and think that you can just go back and reuse those wells. But I have seen incompatible materials in the construction of those systems. And I've also seen where the fact of the matter is wherever the injection interval is from that sparge system does not line up with the contamination at all. I mean, it's below it intentionally, because that's what you want in a sparge system. The other question about the were all my examples persulfate, or did we look at the hydrogen peroxide? That the Liao article, which is again out there, public domain, looked at all four. It looked at hydrogen peroxide, which was the Fenton's reagent. So it gets a little confusing, but if you see Fenton's reagent, that's hydrogen peroxide. It looked at alkaline activated persulfate, and it looked at permanganate. So there are a couple of articles out there that have looked at all the different oxidants, and really you see the same general trend where, and there is some variation because of these residuals, right? With a sulfate residual, you're going to tend to favor the sulfate reducing bacteria. With an oxygen residual from hydrogen peroxide, that's going to favor different sets of microbes. But the bottom line is there is data out there showing the same general trend, a dip and then a recovery following the ISCO application.
Great. So the next question is, beyond TCE reduction, how do you address secondary water quality impacts such as sulfate accumulation from the persulfate breakdown, or if you have heavy metals that are mobilized due to the shift in the redox conditions or the pH?
Okay, so metals mobilization is something that has been relatively well studied. If it is a concern at your site, I would of course recommend monitoring. And again, this is a time frame type of thing that we're talking about monitoring. But if you even take the discussion that we were just having about, monitoring for sulfate reduction, and then even where dihalococoides comes back, you're talking about a recovery to the geochemistry that was originally there. Metals follow Pourbaix diagrams, EH, pH. They're going, as your site recovers to baseline geochemistry, it's going to, of course, return to whatever state they were previously. But I want to add in, as you're forming sulfides, as you're reducing the sulfate to sulfide, sulfides react and precipitate to form very low solubility sulfides. This is actually one of the metals treatment technologies that's out there, is sulfide creation. So if you have a site that you're monitoring and your sulfate is being reduced to sulfide, you're actually going to be, probably creating, you have the potential to be creating metals conditions that are lower than they were at baseline because of all this sulfide precipitation. So that would be the metals. And I'm sorry, what was the other part of the question?
It is, let's see, so sorry, I lost that question. I'm sorry about that, Brant.
Not a problem.
I'll remove that one, but I think you did answer most of it. Was the metals mobilization question of it, and then the secondary, any other secondary groundwater quality concerns that would come up?
Yeah, so this is one of those things it is a good question, and like sulfate is really the primary, sodium and sulfate, or potassium and sulfate are the primary residuals of a alkaline activated or most activated persulfate. Sodium doesn't have many fates, right? It's probably going to be pretty darn conservative in your aquifer. Sulfate has several fates. If you have a lot of calcium, you can get calcium sulfate precipitation. There's a number of other compounds that will precipitate out with sulfate. So there's one mechanism. If you have a reductive aquifer, as we were talking about, you're going to be forming sulfides, and so that's another mechanism. But the other thing that I just want to point out, and this really depends on the size of your site, but I'm a big believer in the fact that even when you're talking about a relatively large site, moderate size site, it's a drop in the bucket when you start talking about the overall geochemistry in the area. And so with time, the sulfate, even if there is not a fate, and there's usually a fate where something occurs to the sulfate, as it's migrating, usually the sulfate concentrations wane in all the monitoring points, and it's just because overall you've got groundwater flushing in, there's groundwater flushing out, and you don't tend to see anything above a secondary MCL for all that long at a site, although of course theoretically possible. I totally agree.
All right. The other question, Brant, is in the Sutton et al. In the Sutton et al. Paper, there was a pH recovery of around 5 that happened after sulfate addition, but it took about 6 months for that recovery to happen. How long have you seen before neutral pH returns so that biodegradation can resume?
So that was an unactivated persulfate, and so that would be most analogous to we tend not to recommend unactivated persulfate at sites just because of kinetics. The bottom line is most aquifers are dynamic. Very few true bathtubs where you can have extended contact time exist, and unactivated persulfate tends to have slower rates of reaction. You tend to need contact times of multiple months, whereas persulfate activation, you need contact time with the contaminant, usually hours to days is the time frame there. So that exact situation is not exactly all that common, but I understand why they tested it the way they tested it. It would be most analogous to iron chelate activation. which is closure 1 mostly. There's organic activation in closure 1 and iron chelate activation in closure 1. And you will see the pH drop. I do want to say the vast majority of applications are alkaline activation, where it is intended to increase the pH. Relatively high pH 12, 12.5, not uncommon to see with alkaline activation. But again, as the persulfate decomposes, it is going to, release the acid because, the sulfate is really sulfuric acid. So it's releasing the acid. The acid reacts with the alkalinity, the pH drops, and we usually are in that kind of neutral range if everything goes according to plan and design. But if you do have a closure 1, it really depends on the site. If you have carbonates present, then it can be quite fast. If you are in a nice silicate aquifer, then it could take a while. I forget exactly what was referenced, but months is probably in the time frame that you're looking at. I'm not sure if I don't recall the pH being too low in looking into the year time frame, but I absolutely know of sites where it was in the months time frame, multiple months, even 5, 6, 7 months for it to recover. This can be evaluated. And there's a base buffer capacity. Anybody that does a lot of alkaline activated persulfate is familiar with that term. There's also such a thing as acid buffer capacity tests, and it basically measures how much buffer resistance your site soils are going to provide. And this can come from carbonates, but it can also come from a lot of different compounds. And that's going to be a predictive element that can tell you how long it's going to persist. But that's also part of our thinking in guiding the people often towards alkaline activation. We tend to use iron chelate activation in closure 1 for low to moderately contaminated sites. But as you start getting higher and higher doses, we actually don't want a site to go as more and more and more acidic. We actually so closure 1 can be used in those higher concentrations. Sure, it is technically effective, but this is one of the reasons why you might skew towards the alkaline activation.
That makes a lot of sense. So on these sites, Brant, you've been discussing a lot of successes where they've been implemented. Are there any conditions or contaminant plumes that you specifically recommend that this is not the appropriate strategy to use?
Oh, wow. That just gets so specific so fast, because we do deal with a lot of atypical contaminants. I mean, certainly as you start talking about any of your fluorinated compounds, just to get this out there, the sulfate radical will react with the carboxylic acid group. So like your PFOA, the parent compound is, or the parent term is PFCAs. So all of those compounds, your PFBAs and all of that. But that, because it's radical only, you would only get any of these reactions occurring in the source zone where you're getting the actual radical formation. It doesn't treat the sulfonic acids, so like your PFOS, which is one of the reasons why so that's an issue, especially with AFFF, just because those are usually commingled. But with the carboxylic acids, heat activated persulfate, a few other things, there's some work out there showing that it works with the carboxylic acid. So, but my point being, you would really be looking at something like that, right? Something where you need the hydroxyl radical or the sulfate radical and to treat the contaminant, but it's not going to react biotically. And there are a large suite of, they're not your typical contaminants, but there are a large suite of contaminants that will only react with the radicals and won't go biotically, aerobically or anaerobically. So that's really what you'd be looking for.
Makes sense, especially compounds we're still learning about, right? We might have to do a little more investigation and research.
Yep.
Okay, last question, and we really appreciate you going a little bit over with us, and we'll wrap it up after this one. This question is that they say, I'd be interested to understand the comparison between the remedial outcomes from the consequential iron sulfate that's generated from the ISCO compared to applying a zero-valent iron, particularly if it's a sulfidated zero-valent iron. And do you have any comparison studies that you guys have done about?
So probably not as direct as that they would like, but what we have found that we actually have webinars on biogeochemical. Dora, I think actually even Dan, maybe it was Alan, Alan Seach, Dr. Alan Seach, presented in one of the Microbial Insight webinar series on biogeochemical. The bottom line is biogeochemical is pretty much that there are actually some advantages to biogeochemical over just straight up zero valent iron treatment. And I'm just going to go to the couple that I like. They react with pretty much the same amounts of contaminants, although there may be an oddball contaminant here or there. Again, this gets into some thermodynamics where zero valent iron is a very powerful reductant, and the iron sulfides may not be quite as thermodynamically powerful, but certainly in the range where I haven't seen a chlorinated compound that wasn't treated by the biogeochemical that was. But theoretically, again, that's possible because zero valent iron is theoretically more powerful than the iron sulfides. But actually, you can look at the half reactions, and I'm just running through off the top of my head, and I'm not thinking of a chlorinated solvent that doesn't have the half reaction above the negative 220 for the sulfate reduction, which is where you kind of need to be to get all those. So I think most common contaminants, they're theoretically equivalent. But the advantage that I really like about biogeochemical is the fact that you put in zero valent iron, and for most instances it's relatively immobile. It's going to wherever it ends up is where it's going to end up. And granted, that might be changing a little bit with the micron size zero valent irons. We've recently started offering the 5 micron iron, and of course the key there is the particle size of the iron is small enough to move through the throat size of a lot of the soils that you have out there. And so that will distribute better. But if you start talking about larger zero valent iron things, wherever they are in place, they're not moving through the throat size of soils unless you're dealing with a gravel. So it's wherever they're in place, that's their contact zone. However fast the groundwater is moving through that contact zone, that's your contact time. Whereas with biogeochemical, basically, you got your volatile fatty acids and everything, all the electron donors that are solubilizing and moving down gradient from where they are in place. You got your iron sources, and the iron is solubilizing and moving down gradient. Same with the sulfate and the sulfur sources, and you're creating these conditions. All of this from the point of which they are applied to some distance down gradient. And we've seen instances where these go quite a distance, not just a couple of feet. We're talking tens of feet, maybe even 100 feet down gradient from wherever they were in place. I mean, it really depends on the site conditions and the aquifer. But so don't hold me to the hundreds of feet, but we're definitely seeing them go down gradient. This creates a larger treatment zone. This migrates into, this allows diffusion to allow these to migrate into secondary and tertiary pathways and precipitate there. And so basically you get this expansion of your treatment zone beyond just where the zero valent iron was placed. So yeah, I actually see a lot of advantages over the biogeochemical over just straight up zero valent iron.
Thank you very much, Brant. And Hannah just uploaded for everybody that's interested in that presentation that Alan did, a link to that webinar that's recorded on our website. So you can click on that link and download that if you'd like to watch that webinar. Brant, thank you very much for staying over with us and for the excellent presentation today. And thank you everyone for sticking with us and asking all these wonderful questions. And we really appreciate all of your time and interest, and we invite you to join us next month for our webinar series. And if you have additional questions, please reach out to Brant or Josephine. I know they're both always available to answer questions that you have, or you can also, if you have questions on the microbial side, feel free to reach out to us at info@microbe.com. But we really, again, Brant, thank you for your time and the wonderful information that you provided to us today.
Great. Thanks, Dora. Thanks, Hannah. Thanks, everyone, for attending.
All right. Have a wonderful day, everyone. Thank you.
Bye.